So today we are going to talk about linearity and superposition. So let me give you guys a brief intro thing here. The superposition principle is something that is regularly taught in circuit theory courses. And we're going to find out shortly that it's actually just a small portion of the concept that I'm going to call linearity. Linearity is not usually taught in circuits classes. It's taught later on in both the electrical engineering and biomedical engineering, and I think the mechanical engineering programs. But it can be directly applied to circuits, and it is a very powerful thing. So I like to go ahead and just bring it up now so that we can apply it to circuits. And in specific instances, it can be very beneficial to us to understand the concept of linearity because it will allow us to effectively simplify circuits in a way that we can get a wide range of results from them without a lot of extra effort. So let's start with the superposition principle. The superposition principle, this is going to be a long sentence, states that in any linear resistive network, the voltage across or current through any resistor or source may be calculated by adding algebraically all the individual voltages or currents caused by the separate independent, and I'm going to underline independent because it is very important, sources acting alone with all other independent voltage sources being replaced by short circuits and all other independent current sources being replaced by open circuits. All right, so this is a whole hell of a lot of text. What I would like for us to do is to work an example and apply this superposition principle. Okay, so There was a spider on my desk. So this is the circuit that we're going to be looking at. Here we have a 6-volt source connected to a 6-ohm resistor. Here is a 10-ohm resistor through which a current IX flows. Over here, we have a 9-ohm resistor. Here we have a 2-amp source. And our goal here is to figure out what the quantity IX is. I'm just going to put out here to the side. IX is equal to question mark. Okay. So let me ask you guys a question. Is this a series of questions actually? Is this a single loop circuit? Is it a single node pair circuit? No. Are there any sources that we can combine? Are there any resistors that we can combine? Really? None of the resistors are in series and none of them are in parallel, so I would argue we can't do any resistor combination here. So for this particular circuit, there is no simplifications whatsoever that we can make with our current level of circuits knowledge. Okay. Additionally, because it's not a single node pair circuit and it's not a single loop circuit, we can't just use KCL and Ohm's law or KVL and Ohm's law. We're actually going to have to use both. So we're going to have to effectively throw the kitchen sink at this problem if we wanted to solve it as it stands. So let's do just that. Okay. So what I'm going to do is I am going to identify some currents here. So I'm going to call this current I6, and now effectively every current in this circuit is identified. And I'm going to identify some voltages as well. So I'm going to call this voltage V6, and I'm going to call this voltage V10, and I'm going to call this voltage V9, like so. And while I'm at it here, I could call this the voltage drop over the current source. I'm not actually going to wind up using all of these things, but I'm just trying to identify everything that I can, and then I'm going to develop some relationships. Okay. So because I've done this exact problem a multitude of times, I am going to do this in the easiest possible way. Okay. So the first thing that I'm going to do is I'm going to write a Kirchhoff's voltage law loop, or Kirchhoff's voltage law equation around this loop. Okay. So that's going to look like -6 volts plus the voltage V6 plus the voltage V10 is equal to 0. I'm going to write a Kirchhoff's current law expression at this node. So I'm going to say that this current plus this current plus this current all sum together to make 0. So that's going to be negative I6 plus IX minus 2 amps is equal to 0. And I've written 2 equations and I currently have 4 unknowns. So what I'm going to do to relate those unknown quantities to each other is apply Ohm's law. Sorry. So what is the relationship between? Yes. Ix is positive, so I'm adding those three green currents together and setting them equal to 0. Since I6 is in the opposite direction as the green arrow that represents that, it gets a negative sign. Since the 2 amps is in the opposite direction as the green arrow, it gets a negative sign. Because Ix is in the same direction, it gets a positive sign. All right, so now I'm going to use Ohm's law in order to express V6 and V10 in terms of the currents I6 and Ix. So using Ohm's law, we can say that V6 is equal to 6 ohms times I6. Excuse me. And using Ohm's law, we can say that V10 is equal to 10 ohms times Ix. And what I'm going to do now is I'm going to substitute these Ohm's law relationships into my Kirchhoff's voltage law relationship and do a little bit of algebraic manipulation. Okay. So V6, 6 ohms times I6 plus V10, 10 ohms times Ix will be equal to 6 volts. And slightly rearranging my KCL expression, I will have negative I6 plus Ix is equal to 2 amps. And I now have a system of equations that I can solve. Now we could do this using substitution, but that takes time and I am lazy, and I have suggested to you all heavily at this point that you should buy a calculator that is capable of solving systems of equations. So let's use our calculator to solve this system of equations. You are unsure of how to solve a system of equations using your calculator, please let me know. So in my first equation, my coefficient for I6 is positive 6. My coefficient for Ix is 10, and my constant term is 6. In my second equation, my coefficient for I6 is negative 1. My coefficient for Ix is positive 1, and my constant term is positive 2. And when I solve this system of equations, I get I6 to be negative 7/8 of an amp, and Ix to be positive 9/8 of an amp. For those of you, Hannah. All right. Okay, so let me help you grade first. What kind of calculator do you have? You have a CI so specifically the CI 36. I honestly don't know if the CI 30s and but for the CI 36, if you hit second and then you hit tangent, the system falls within. This is a 2x2 system. We'll put 1 or anything, and then now we have primitive elements. Exactly what it will do. All right. Hannah, what type of calculator do you have? All right, so for the Casios, I'll borrow this real quick. You will go to the menu key and you need to go down. Yes. Simultaneous equation. We're solving a system of simultaneous equations with 2 unknowns. And now you can enter in the coefficients. So this is the coefficient of I6, coefficient of Ix, constant term. Anybody else need to learn how to use their calculator? All right. Go down to one of your equations. You're solving simultaneous equations. You're solving two. All right, so for this Casio, you go to mode, hit 5 on 4 equations, and then you hit, this is number 1 is for 2 equations, 2 unknowns, 2, 3 equations, 3 unknowns. This solves polynomial, this solves number 1. Anyone else need help with their calculators? All right, take a moment here and get the results that I got. Okay. So why are the 9 ohm resistor and the 10 ohm resistor not in parallel? Because they share the topmost, that top middle node, but the bottom node isn't the top right node because there's a current source between them. So if we identified our nodes with colors, they wouldn't be between the same color, right? That top right node and the bottom node are not the same. Right. Yes, ma'am. I chose the negative polarity on the left because I know that 2 amps of current is flowing into it. So that was just a way to force that voltage drop if I needed it to be positive. That's it. Yeah. Yeah, so I just moved the 6 volt to the right hand side. So in the calculators, how it works is effectively you have, let me give you guys a very minor crash course in matrix manipulation. Okay. So we're using our calculators to solve these systems of equations. And this is effectively the format that it is expecting. Okay. So I'm going to call this A1 and A2. So these are the coefficient. Actually, let me. So we're going to have A1 here, B1 here, A2 here, B2 here. This, good God, is our first variable, which I'll call it X1. This is our second variable, which I'll call X2. And this is our constant term, which I'll call capital K1 and capital K2. So using matrix map, we would have A1 X1 plus B1 X2 is equal to K1, and A2 X1 plus B2 X2 is equal to K2. So I need my constant terms to be on the right-hand side of the equal sign, and all of my variable terms and their coefficients to be on the left-hand side. So that's why I wrote these equations in this exact form, because that's exactly how I'm going to put it in my calculator. The system solver in your calculator, if you weren't going to use actual matrix calculations to do it, is also in this exact form, where you have your coefficients for your variables on the left and your constant term on the right-hand side of your equal sign. So I have gotten into the habit of writing equations of this exact form so that I make sure that all of my signs wind up being correct when I put them into my calculator, because if the signs aren't right, the system isn't going to get solved correctly. So, yeah, this, just to be clear here, I substituted these relationships into this equation, and then I moved the constant term to the right-hand side. For my KCL equation, all I had to do was just move the constant term to the right-hand side. All right, so we have solved this circuit using a system of equations. Hopefully we have all gotten the same answer at this point. this wasn't, as a jackass with a PhD, this was not particularly difficult to me, but I could understand with you guys' limited amount of circuits experience how this 5-element circuit is probably one of the hardest things you've seen to this point, because we can't use just simple KCL, simple KVL, Ohm's law. We can't combine resistors, we can't combine sources or anything like that, okay? We had to wind up setting up a system of equations, which can be a bit of a pain in the butt. Now, let us apply the superposition principle, okay? So I'm going to redraw this circuit, and I'm going to take a note here. These are the results that I got. In particular, I'm interested in the quantity Ix, and we found that with both sources on at the same time, Ix was equal to 9/8 of a volt, okay? So I'm going to redraw my circuit. And once again, we are going to be solving for the quantity Ix, okay? But we're now going to do it in an entirely different method that utilizes the superposition principle. So what the superposition principle really states is we can analyze this circuit with each source on by itself and then add the results together at the end and get the same result as if we had analyzed the circuit with all of the sources on at the same time. So I'm going to now prove that to you, okay? So our first case will be with our voltage source on and our current source off, okay? So our voltage source on, we still have our 6-volt source. Here's our 6-ohm resistor. Here's our 10-ohm resistor. Here's our quantity Ix. I'm going to call this Ix prime because it isn't all of Ix. This is our first iteration for calculating it. Here is our 9-ohm resistor. Now, we need to turn our current source off. How do we do that? Open circuit, absolutely right. So an off current source is replaced by an open circuit because that forces 0 amps of current to flow. That is also exactly what the superposition principle tells you to do. If you look at the very last little bit, all independent current sources are replaced by open circuits, okay? So I'm just going to throw some open circuit terminals here, and we are going to solve for the quantity Ix. Would anybody care to take a stab at solving for Ix prime? So 6 volts divided by 6 ohms plus 10 ohms, spelling out a little bit more, Kevin, but you're absolutely correct, is equal to 3/8 of an amp. Why am I able to say that the current Ix prime is the current that's flowing through the 6-ohm resistor when it's defined to be the current that's flowing down through the 10-ohm resistor? I'm sorry, what? Why do you consider them as if they're in series though, John? You're correct, but explain it slightly better. How much current can branch off and flow through the 9-ohm resistor? None, because it's not part of a closed current carrying loop, right? So if none of the current can branch off and flow through the 9 ohm resistor, the only current flowing in this circuit is Ix prime. Does that make sense? All right. So now let's look at case number 2. Our voltage source will be off and our current source will be on. So to turn off a voltage source, what do? Short it out. So my voltage source has been replaced with a wire. Here I have my 6 ohm resistor. Here I have my 10 ohm. I'm going to call this current Ix double prime because it's my second iteration of my superposition process. How can I find Ix double prime? Current division, absolutely. If you didn't suggest that, that's what I was going to tell you to do in a moment, okay? You could absolutely use a couple of other different things, but current division is the easiest way to do it here. So if we apply current division, we're going to have 2 amps multiplied by the ratio of 1 over 10 ohms divided by 1 over 10 ohms plus 1 over 6 ohms. So let's see. So that's going to be 3/30 over 3/30 plus 5/30 is 3 over, sorry, 3/8 times 2 is 6/8. There we go. I was doing it right. I was just forgetting to multiply out in front there. So 6/8, by all means, throw it in the calculator if you don't trust my mental math. And now we can say that Ix with both sources on is simply the sum of the Ix's with one source on at a time, or Ix prime plus Ix double prime, which is going to be 3/8 of an amp plus 6/8 of an amp, comes out to be 9/8 of an amp. Is this the same result that we got with both sources on at the same time? Yes. Was the circuit analysis that we did using the superposition principle easier than when we treated the circuit with both sources on at the same time? In this case, I would argue yes. An Ohm's law relationship and a simple current division relationship, and then we added the results together, okay? This will not always be the case. It depends on the circuit that we're looking at. Hannah. All of the 2 amps of current flows through the 9 ohm resistor before splitting up. So this current right here, yeah, all 2 amps flows through the 9, and then it sees that parallel resistive network. So because the 9 ohm resistor the current doesn't split as it travels through it, so it shouldn't be in our current division relationship. Okay, so I'm going to make a little table here, and I'm going to bring the table along with us as we talk about other things, okay? So on the left-hand side, I'm going to label this inputs. And on the right-hand side, I'm going to label this outputs, okay? So when we had a 6-volt source and a 2 amp source exciting our circuit, we found out that our output was 9/8 of an amp. When we had a 6-volt source on by itself, we found out that our output was 3/8 of an amp. And when we had the 2-amp source on by itself, we found out that our output was 6/8 of an amp. So these are the 3 different cases that we have looked at thus far for our circuit. And I am going to copy this. All right. So we have talked about the superposition principle. We have now applied the superposition principle. Let's switch gears slightly and talk about the concept of linearity. So I'm going to introduce something to you guys that I don't know that you've seen yet, and you're going to be annoyed with me whenever you see it, but I use it for a reason. And this thing that I'm about to draw is what's called a black box network. And all this black box network represents is a circuit or system to where we don't necessarily know what's inside of it, okay? So I'm using it for a general purpose thing here, okay? On the left-hand side of my black box network is where I'm going to apply my inputs. So I could apply some input, x1 of t. I might apply some secondary input, x2 of t. And on the right-hand side is where I'm going to take my outputs. Y1 of t, and Y2 of t, okay? So this is just, for our intents and purposes, a different way of looking at circuits. Instead of looking at from a component level, we're looking at it as a system level diagram, okay? So if this system is linear, or this network is linear, the system response or output must satisfy the following relationship. Okay. So before I give you the relationship, I need to put one other thing here on our diagram, and that is our system's transfer function, h of x. So this function effectively describes how the system acts on the inputs to give us the outputs, okay? So for a linear system, we would have the following relationship. H, open curly braces, of alpha x1 plus beta x2 will be equal to alpha y1 plus beta y2, or H acting on x of t will equal to y of t. Now there are 2 distinct and independent properties that are wrapped up in this gobbledygook mathematical expression, okay? They are the additivity property and the homogeneity or scaling property. Okay. So effectively what this mathematical expression says is that if I have some inputs, x1 and x2, and I scale those inputs, x1 being scaled by a factor of alpha, x2 being scaled by a factor of beta, and my system acts on them, if this system is linear, the output will simply be alpha times y1, the output caused by x1, plus beta times y2, the output caused by y2, or I can treat it as if I have a total input x of t that is equal to alpha x1 plus beta x2, it generates a total output y of t that is equal to alpha y1 plus alpha y2. Okay, a lot of math magic going on here that you guys don't necessarily need to understand right now. We're going to talk our ways through it. Okay, so as I mentioned a moment ago, there are two distinct and independent properties that must be satisfied: additivity and homogeneity. Let's talk about the additivity property. Additivity property of linearity. Okay. So the additivity property of linearity says if several independent inputs are used to excite a system, the total response, where response is just a fancy word for output, due to all of these excitations can be determined by considering each input separately while assuming all other inputs to be 0. Does this sound vaguely familiar? It is literally the exact same thing as the superposition principle. No difference whatsoever. This is just a more generic form. Okay. So we don't need to prove the additivity property of linearity for a circuit containing resistors and sources. We've already done it. Okay. So we're good with this part. Now let's talk about the homogeneity or scaling property of linearity. So the homogeneity property says if an independent input is used to excite a system, scaling that input by an arbitrary factor alpha causes the output to scale by the same amount. So let's see if this is true. Let's take our circuit. But this time, let's scale our inputs, our voltage source and our current sources by a factor of 2. So let's turn our 6-volt source into a 12-volt source. We're going to leave the directions and stuff like that alone. Here's our 6-ohm resistor. Here's our 10-ohm resistor. Here's the quantity IX. Here's our 9-ohm resistor. Here's our 2-amp source. Let's see. Here is V6. Here is V10. Here is I6. If we write KVL equation around our leftmost loop, we'll find negative 12 volts plus V6 plus V10 is equal to 0. If we write a KCL expression for our top middle node where the currents that are leaving the node are positive, we'll have negative I6 plus IX. Sorry, this 2-amp source should be a 4-amp source now since we're scaling it by a factor of 2. My apologies. Minus 4 amps is equal to 0. Our Ohm's law relationships will be the exact same as they were the first time we looked at this, where V6 will be equal to 6 ohms times I6, and V10 will be equal to 10 ohms times IX. Substituting those relationships into our first equation, we get 6 ohms times I6 plus 10 ohms times IX is equal to 12 volts. In our second relationship, we're going to have I6 plus IX is equal to 4 amps. And we now have a system again, so let's solve this system. So for me, all I have to do is just change the constant terms in the system that I have stored in my calculator, right? So this is the exact same system that we were solving earlier, except that the 6 we had as a constant value is now replaced by a 12. And the 2 that we had in the constant value is now replaced by a 4. And if I solve this system, I get I6 is negative 7/4 of an amp, and IX is positive 9/4 of an amp. Okay. So I scaled my inputs by a factor of 2, and my output scaled by a factor of 2. So this circuit and any circuit containing only resistors and resistors and voltage and current sources satisfies the homogeneity or scaling principle. Okay. Now let's bring our table back into the fold here. So just as a quick observation, when we applied twice 6 volts plus 2 amps, we got twice 9/8, which was 9/4 of an amp. Okay. So the last thing that I want to do here is to apply both the additivity property and the scaling property simultaneously, okay? And so I'm going to make a prediction. So let's say that we scale the 6-volt source by a factor of 5. And we scale the 2-amp source by a factor of 3. What would we expect our output to be? So when we had the 6-volt source on by itself, we got 3/8 of an amp. So if we scale that 6-volt source by a factor of 5, that 3/8 should also scale by a factor of 5, giving us 15/8. When the 2-amp source was on by itself, we got an output of 6/8 of an amp. If we scale the 2-amp source by a factor of 3, then we should get 3 times as much output. So 6/8 times 3 is 18/8. If I add these results together, 15 plus 18 is 33. And so my expectation here is that I will get an output of 33/8 of an amp if I scale the voltage source by a factor of 5 and the current source by a factor of 3. Okay. So let's check whether I'm right. So if we put a 30-volt source here, and a 6-amp source here, let me define my currents and voltages. If I write my KVL expression, let's skip ahead slightly. This is going to look like 6 ohms times I6 plus 10 ohms times IX is equal to 30 volts. My KCL expression, I'm going to have negative I6 plus IX is equal to 6 amps. And let's solve these guys, particularly we're interested in IX. So 6, 10, 30, minus 1, 1, 6. And when I solve this system, I get 33/8 of an amp, the exact thing that I predicted would happen. So this circuit is a linear circuit that satisfies the additivity property, also known as the superposition principle, and the homogeneity property, okay? I'm done here. I want to show you guys your in-class assignment for a moment to explain exactly what I'm talking about there, but I do want to make a point to you guys that we did not cover an example like this in class today, but you will see at least one on your homework that contains a dependent source, okay? So everything that we've dealt with here today dealt with turning off independent sources, okay? So if you ever have a dependent source in your circuit, you can never turn it off. Dependent sources are always on. Independent sources are the one that you turn off in your analysis when applying superposition, okay? All right, so I want to open up your in-class assignment here really quickly. This is in-class assignment number 5, if I'm not mistaken. All right. So this is how I word superposition problems. I'm making a point to tell you this because on your exams, I don't tell you, use nodal analysis and do this, or use superposition and do that. I just give you a circuit and ask you to solve it, okay? So whenever I say determine the contribution of a particular source to the quantity, blah, 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 I'm expecting you guys to use superposition. So for part A here, determine the contribution of the 1 amp current source means leave the 1 amp current source on, turn off all other sources. Similarly, in part B, determine the contribution of the 5-volt source means leave the 5-volt source on, turn off all the other sources, solve for the quantity. In part C, I do not expect you to do any circuit analysis whatsoever. Simply use the results of parts A and part B, add them together, and you should get the answer for part C. Similarly, in part D, I tell you that if the voltage source were replaced with a 3-volt source, meaning that it's scaled by a factor of 3/5 or 0.6, and the current source were replaced with a 2.5 amp source, meaning it's scaled by a factor of 2.5, tell me what Vx should be. Again, there should be no need for you to do any circuit analysis whatsoever. Simply take your results from part A and B, scale them appropriately, add the results together. That is the beauty of linearity. If we understand how the circuit works with a 1-volt source and a 1 amp source, we understand how it works for any possible combination of sources that we could apply. Okay. All right. That is enough ranting out of me for the day. So work on the in-class assignment problem. And then if you need any help, please let me know.